Welcome to a lesson with Dr. Powell. Let's take a look at an example of running a Graham-Schmidt process and how it's done. So, how do we get from a starting set of vectors to our ending set? Well, the first vector here in our ending set is the first vector in our starting set. Our second vector, how do we obtain it? Well, we're going to be using vector projections in this example. And essentially what we do is we take the second vector here and we subtract off a multiple of the first vector of our result. It's like one, so what's previous to where I am in my result, okay? Um, and before we talk about that, let's just kind of fast forward and look at how we obtain the last guy. The last guy is actually the last guy here in our set. Subtract off a multiple of what I have in my result so far. So before this guy. So a multiple of this guy, and then subtract a multiple of that guy. So we just got to figure out how to get the right multiples. All right. How do we get the multiple that we need to multiply to this one? When we subtract off that and the multiple to that we put on with this one um, that we subtract from this as well to get this guy. So those multiples just have to do with projection, all right? So kind of what we're doing is we're taking this guy. Okay, so let's go back to the second case. So how do we get this guy right here? We take the second vector here, and we're going to project it onto this guy. And then we subtract off the projection. So there's no more projection on there, and so it's orthogonal. So you take away all projection, so there's no projection, and then therefore it'll be orthogonal. That's the basic idea. And you're just kind of incrementally trying to make it orthogonal to each one as you go. So, um, um, so how do you do that? Well, right here, first projection length. Projection length is simply dot product with a unit vector that's in the direction that you want to project to. Suppose u is like your ground right here that you're projecting to. So v kind of comes right down here, and that's the projection length right there. And so this dot product v dot this unit vector, where we take u and divide by the its length, that would be this projection length. But then we need to multiply this to the actual unit vector here. So we rescale this unit vector up to this spot, so we get this whole vector here. So we actually get the projection as a vector, so that when we subtract it, so we take v and we subtract off this. In fact, visually, this is quite nice. Visually, this is very nice because, imagine subtracting off this vector. So kind of going backwards. So from here back here, look at that. Take this vector, subtract it off that projection. Don't we get something orthogonal? So we replace v with that guy, that's orthogonal. Visually, it's actually quite nice to subtracting that off. So that's kind of what we're doing. Now here, that's the calculation for how it's done. Now, you can rewrite this process, put the u's together, using the idea that this is simply the sum of squares, which is just u dotted with itself. And then you just have u dot v, and you're multiplying by u. So this actually is a scalar right here. That's the scalar that you need. Just take a dot product, and then you divide by the ground dot product with itself. So right here, let's try that. So this guy dotted with that guy. I think there's lots of zeros here, and we only get a 1 out of this, so it's just 1. And then you divide by this guy dotted with itself, which just ends up being 1 plus 1, so 2. Okay, so that's how we get this. If you check this, this calculation gives you this precisely. Okay, let's go to the next guy. So we're going to take this one, and we're going to, what do we multiply onto this guy? Well, we think of this guy as the ground, and we take this dotted with this. Notice when we do that, we just get -1. Then when this is dotted with itself, we already have that was 2, and so there's our coefficient. Okay, now the next guy we take this one and we dot it with this one, because Notice we're trying to get a multiple of this guy. So take this guy dotted with that one, and if we do that, we have what? 1 minus a half. That's the only things that really survive. So which is just positive a half. So that's that dot product. And then you just take the dot product of this guy with itself, which is 1 squared plus a quarter squared, or plus a quarter, sorry. 1 squared plus a quarter, because it's a half squared plus a half squared. So, and which ends up being 1.5 or 3 halves. So we have 3 halves right there. So that's our coefficient. So noticing this is like 3 times a half on the bottom and a half on the top, the halves cancel. So you just have 3 in the bottom, just a third. The third moves on the inside. You could rearrange it like this. You can rearrange it like that. Now, if you do this addition process of vectors right here, you obtain this precisely, which is exactly what we wanted. So this is a little example of Gram-Schmidt process using vector projections. Thanks for watching.